I think that's the best way rather than putting all the lecture note there. So you will see the lecture note one by one. As the syllabus showed, there are around 17 lectures. So what I will do in the class, I will basically explain this lecture note. That's what I will be doing in the class. So if you read the lecture note beforehand, the lecture note will be always available beforehand. If you read it, and then it will be very useful in the class. If you read it before and then if you don't understand something, you can ask the question in the class. That would be, that would be useful. That way you can make the class more useful. Okay, so if you just looked at the lecture notes, it was already available. What I'm going to do, I'm going to explain some of the concept. I'm going to explain computer analysis using this example. So let's say we want to solve this equation. Let's say we want to solve this equation. Now, there are three ways to solve. I mean, there are many ways to solve this equation. But one is the analytic method. So you just if you can factorize it, then if it is x squared minus 7x plus 12, you can factorize it using x minus 3, x minus 4 times x minus 4 is equal to 0. Then the solution is, solution is x is equal to 3 or x is equal to 4. So that is the analytical method. The graphical method, now again, we had to do this by hand. So for graphical method, we will plot this curve. Then we are going to use some intuition here. So it is a quadratic equation, so I know it's going to look like a parabola. And the point is, when y is equal to 0, so that's the equation. So I'm basically plotting a graph here. So the y is x squared minus 7x plus 14. So I know this is going to look like a some parabola like this. What is this point? To find that point, you let y is equal to 0, and that point will be when x is equal to 0. So this point is when x is equal to 0. You substitute x is equal to 0, and then you get y is equal to 14. So we know that this point is 14. And then we know that it is a parabola, so I will just sketch. So how would I sketch this? Well, I will assign some points for x. You don't need to know y is equal to. I will just I will select some x point, x values. So basically, I will create a table. I will create a table. Sorry, I will create a table of xy points. I will create a table of xy points. xy, x is equal to 10, minus 9, minus 8, over 20. Okay, so you create all these points, and then for x, this point you can find y. So you have a pair of points, and you just enter them here. I should do that. So first you enter the points. First you will enter the points, and then you will connect the dots using a line. So now you have. So what is the roots? Roots is when the graph, when y is equal to 0. These are the roots. So maybe I will call it root 1. Okay, so that will be root number 1, and that will be root number 2. So this since it is a quadratic equation, we know that it has two roots and of the root. So we will just, if you sketch it for scale, then if you find out where it becomes 0 at this point, then we just observe it, and we can observe it and tell that is the rule. The other one is so now let's see the third approach, computer-aided solution. If we have to program a solution, how that's going to work. So once again, the problem is fx is equal to x squared minus 7x plus 12. Now, if we have to program, we need to use some other knowledge, and this is in a form, we will notice that this is in a form a x squared plus b x plus c. Now, if you have an equation in that form, you already know the formula. Formula is x is minus b plus or minus square root of b squared minus 4ac over 2a. So we can say x1 is minus b plus or minus square root of b squared minus 4ac over 2a. x2 is minus b minus square root of b squared minus 4ac over 2a. That is one approach. So then, but if you have an equation like fx is 14 x to the power 7 plus 2x5 plus 3, then we don't know a formula for that. So then probably we can do some iterative methods. So we'll say we will write a function xk is a function of xk plus 1, xk is a function of xk minus 1. So this is a previous guess, and then that is present. And then we will iterate it for this. So that is we can program, this can be programmed in a computer. This can also be programmed in a computer if you know A, B, and C, and you just write the solution. That's a very easy program. But this is called root finding. You know, I think we have 3 lectures dedicated for this root finding. You know, for different type of complex function, how to find roots. So that is one way of introducing computer analysis. You know, in a way, the whole class is an introduction to this. So I will go to another examples now. Yes, there's an iterative approach with lectures 5, 6, 7, I believe. So we will go, you know, more detail into that. So I just took this example to give an introduction to a manual hand, you know, based solution. For example, to do this type of solution. Can you see my mouse? Can someone see if you can see my mouse? Probably not, right? Okay. So I will point to this. No. Okay, good. So this analytical solution, you know, as you can see, it is limited. You know, what if we couldn't factorize? You can factorize. If you cannot factorize, you cannot do a graphics solution. You cannot possibly draw a very complex graphical solution. So that's not possible either. So computer analysis, but you will see it is possible for long many different applications. Now, so that's one way of introducing this class, over what is computer. But this truth finding will come into very detailed lectures later. Now let's go to, again, I'm following the lecture note. I'm pretty much following the lecture note. So, if hopefully from next time you would come after reading the lecture note, so you'd be a bit more comfortable. Now, this is another example. So this time I'm going to introduce an engineering problem. So let's think about a hot air balloon, which you are seeing on the screen. That's a hot air balloon I managed to sketch just before this class. Now, what we are going to do is we are going to, usually the hot air balloon, it floats in the air. So why it floats in the air is the forces acting on this hot air balloon, if it is the same. So there are two important forces acting on this hot air balloon altogether. So one is the gravity, the weight of the whole thing, the balloon, the basket, and the weight of the people in the basket, everything combined. So that is going to act downwards, that force. And then the resistance, air resistance, since it is a, the balloon is holding a gas that is lighter than the air, so it wants to go up. So it will just, it will give a force on the opposite side. So that's, we will call it the air resistant. Now, it is known through physics that the gravity is mg. Okay, m is the mass, g is the gravitational acceleration. So let me write that. So m is mg, where m is mass and g is gravitational acceleration. So that is meter per second square. That is usually kilogram, the unit of them. Now, air resistance, again through physics, air resistance is known to be C times V. So C, I'm going to call C is a constant. And then V is the velocity. So when I say velocity, I am assuming the balloon is moving in this direction. It is the movement of the balloon. So that's, just assume for a second that it's moving in this way. So let's assume these are the two forces acting on it. One is a gravity, other one is air resistant. So if that is the case, there might be other forces acting in reality, but let's assume only these two. So if that's the case, the resultant force on the balloon is gravity on one direction downwards, and then air resistance on upwards. So the resultant force on the downside will be this F gravity minus F air. So our goal, so what we are trying to do here, so our goal to find the velocity of the balloon at a certain we're going to make several assumptions. Always in engineering, we make, at least to study, we make assumptions. When you go and apply in real world, then if you know about all the assumptions, then you can make approximations, engineering world approximations. So assume the balloon is moving down. one is moving down. And then this is an important assumption, initial velocity so we assume that the initial velocity was, so it was just staying still and then started moving down. Maybe, you release some gas or something. So it was staying still and started moving down. What is the velocity at a given time? Obviously, based on how the forces act, the velocity is going to increase, especially when it goes down. When the gravitational net force is high, is going to with the acceleration, the velocity is going to increase with time. So what is that? Okay, so for that, we're going to do some math. Okay, so from this equation, we have F is resultant force is F is F gravity minus F air. F is F gravity minus F air. And F gravity is mg. We just saw that. F air is cv. That is. And then through Newton's second law, we have F is equal to ma. That is force, that's mass, acceleration. So if we use that, we can write this is ma. So the acceleration from this acceleration is mg minus cv over m. So that will be g minus cv over m. So we have a formula for acceleration. So that is acceleration. Now, we also know that what is by definition acceleration is the rate of change of velocity. Velocity is the rate of change of displacement. So 1 degree higher. So acceleration is the rate of change of velocity. Okay, so I can write A as dv by dt. So v is velocity. Remember, our goal is to find the velocity of the balloon at a certain time. So that is the engineering problem that we are trying to solve. So somehow I related acceleration, which is here. We derive the acceleration, and I related that to velocity. So I can so these are the same thing. So for both, we use physics. Now, so using these, I can write dv by dt. dv by dt is equal to mg minus cv. Sorry, we have simpler form. G minus cv cv over n. All of these came from physics. Now, this is a differential equation. So this is a differential equation. Now, for differential equation also, if it is a simple equation, there is analytical solution. So you can solve this differential equation analytically. I'm sure you took this last year, so probably this is one of the easiest differential equation you had, and you probably solved difficult ones too. So anyway, the analytical solution, it can be solved analytically too, but that is not the point on this class. But let me show what is analytical solution is. So, because if you know the analytical solution, we can always compare that, because that is the ground truth. That is the true value that's going to give. So the analytical solution, for your information, analytical solution. So remember, we are always solving for V. So Vt is Gn over C 1 minus e to the minus C over m times T. So that's analytical solution. Okay, now we will keep that for comparison. Now let me go back to this equation one more time. So we have dv over dt is equal to G minus C over M times V. We are going to solve this using a computer approach. Let's solve this using programming or computational approach. I don't want to say program, because there's a slight difference between programming versus computational solution and algorithm and programming. So I would call it computational method. Now, for this, we are going to use an approximation. Now, dv by dt is, if you just think about the definition, I mean, we will derive this formally using Taylor series, I believe, in lecture 3. But right now, I'm going to just, we're going to use some intuition. So what is dv by dt? dv by dt is the rate of change of velocity. So if we have v t plus 1 here, I'm just showing different values t, and let's say this is time axis. So you have a time here t1, so that will be vt1, vt1, and then so this will be t1, and then let's say another time you have t2, so that will be vt2. Okay, so dv by dt is vt2, the gradient, tan theta is that is the dv by dt, but you can approximate it. So approximately, at that time, dv by dt at that time will be vt2 minus vt1 over t2 minus t1. So this is the intuition that we are going to use. So if we substitute this, dv by dt is v ti plus 1 minus v ti over ti plus 1 minus ti. So what I did here is I just wrote that in a general form. So Ti, okay. So VTI. So this might get a little bit confusing now, but once again, I'm just introducing computer analysis here. This will all be revisited and it will all become very clear. But I mean, again, this is not very complicated either. Okay, so now I have, I used to have a numerical, like a physics-based differential equation, but now I have an approximation for that. So for this, I'm going to substitute VTI plus 1 minus VTI over TI plus 1 minus TI. You should, from my past experience, the students kind of get confused from this step. Where, I had T2 minus T1, T2 and T1 I had now, all of a sudden I made that in a TI plus 1 and TI. So because it is going to iterate, T2 can be anything. T2 can be 10 seconds, T1 can be 5 seconds, T2 can be 100 seconds, T1 can be 90 seconds. It depends on how we define that. So probably to give some more illustration, I should say, let's say this is the t-axis. And let's divide the t-axis. Always t will start at t is equal to 0. And then let's say we divide t into 5-second interval. That will be 5 seconds, 10 seconds, 15, 20, 25, 30, 35, 40. So then, if the present time, if this is t1, this is t2. Or if this is t1, if this is t2. But it depends on how we assign numbers. So usually we will assign t1 for the starting time. So that would be, usually we will call, now again, it can be any method, but it will be t0, t1, t2, t3, 4, 5, 6, 7, t8, something like that. Now using that, we can, for any t, we can write the formula. So let me substitute it there and write that. If you substitute this formula, if I substitute this formula over here, I will get, after substitution, we get VTI plus 1 is equal to VTI plus TI plus 1 minus TI times G minus COM VTI. That's the equation that we get after substitution. Now, if you notice, this quantity, this is new velocity, and this is old velocity. Rather than calling it new velocity, I should call it velocity. I mean, it is both applicable. Velocity at time ti plus 1. And this will be velocity at time ti. Ti is the present time, ti plus 1 is the next time. So this is where, some of the programming concept, it might take a while. This concept is going to be slightly new for many of you. So, the suggestion I would give is, read the lecture note. All of this I'm saying now is available in the lecture note. So that should settle it. But then if you are ready with understanding these lecture notes, then this very same example we will implement in a program in the lab. So after that, you'll be very comfortable. with this concept. So anyway, now let me give some example how to solve this. So first of all, let me do ti. Let me give some numbers ti. So it is ti is 0, 2, 4, 6, 8, 10, 12. So for this ti, we are going to compute vti. So probably I should also I'm going to call this T0. One second. Have a different color. Okay. So this is T0, T1, T2, T3, T4, T5, and T6. So basically we need to compute VT0 to VT6. If you call this T1, T2, T3 up to T7, that is not a crime. Okay, 2. And you will see that in different, we are only going to concentrate on one programming language, but different languages use different indexes. So it might again be another point of confusion slightly, but we will stick with the C++. Now, let me do, so if I want to compute, let's say, let me write this equation that I'm going to start this equation using these notations. So let's say I want V2. V2 is directly, I'm just substituting here. Instead of Ti plus 1, I am substituting V2. So V2 is V. The previous time is 0. See, if the present time is 2, previous time is 0. So V2 is V0 plus Ti plus 1 minus Ti, which is present time minus previous time, is 2. 2 G minus C over M V0. For the very first time, so this is called the initial condition. Now we need to know what is the initial velocity. If you just go back to my problem definition, I said our goal is to find the velocity of the balloon at a certain time. And we also assumed, importantly, that the initial velocity is 0. So without that assumption, we won't be able to solve this numerically. So we need to know V0. So let's say V0 is 0. It could be. So if it is 0, then you just substitute 0 and you have your answer. Obviously, we need to know G, C, and M. So I should probably put that as an assumption too. The values of G, C, M are known. No, G is a gravitational acceleration. Roughly it is 9.8. C is the constant friction constant. If this balloon moves down fast, this balloon, you can just intuitively you can see. If the balloon goes in a high speed, the force, the air resistance will be high. It is proportional to the speed. That's why it is C times velocity. If the velocity is small, it will be small as well. Okay, so if you know G, C, and M, then you can compute the velocity at time 2. Similarly, I can write equation for velocity at time 4 will be velocity at time 2 plus 2 times G minus C over M V0. sorry, not V0, V2. V2. So V2, we just computed here. You can just substitute. Just computed V2, so you can just substitute from there. Similarly, V6 is V4 times 2 times G minus COM V4. V8, V6 plus 2 times G over COM V6, like that. So what we did here, we had an engineering problem. We used some physics, our knowledge of physics, to model that problem, and then we also our goal was to find density with these assumptions, and so we used physics to come up with this differential equation to represent this problem, and then we found an approximation to solve this differential equation. So basically here we solved the differential equation. So if you go through our lecture notes, you will see, I think in the last very few lecture notes, it is even one of the advanced, not really advanced, all the lectures mostly are independent. I can teach any of them in any order. But this happened to be coming at the very last of this lecture series, where we will be solving different kinds of differential equation. Here in this lecture, we solved a practical engineering problem. We formulated it as a differential equation, and we used computer method to solve it. So I showed this how this iteration happens, but in the next class and through the labs, we will see how we will program this, how we will write an algorithm, and how we will program this. So that will be in the next classes. So that's it for today. And if you have any questions, about that conflict, I'll talk to Dr. Maasos, and I will get back to you, to those who emailed me. Other than that, do you have any questions about this class in general, about today, or any future? I should tell you that you can. I am available by email. My email is there in the syllabus. About the labs and tutorial, you can also contact GA. And I'm also available on Wednesdays at 2 to 3 to talk to you, to answer any questions in the Blackboard site, in the form, in this place called, there is a tab for office hours, instructor office hours, so that's also there. Any assessment number, can you explain the number line, please? Are all the labs available right away? What do you mean number line? Come on.
I think he's talking about how you divided it into like certain time intervals. I think that's what he wants. His question.
Okay, I see. Okay, I mean, as I told you, that is one of the confusing part. I mean, it will take some time. So let me see how I can extend. So then, what other questions were there?
So you would decide a time interval, right? But you just have to follow it throughout the equation.
Yes,
right?
Yes. For example, let me write a different time interval. For example, I can write time interval 0. Or you want it, okay, let me write an irregular time interval. So initial time is 0. It can be anything, but or should I write a non-zero initial time, so it will be even a little bit more complex. Let's say time, Ti, is 2 seconds, 5 seconds, 10 seconds, and then 20 seconds, and then, I don't know, 35 seconds, and 40 seconds. So let me call this, I mean, that's a good question. It will take some time to grab this. I can tell you. This is kind of a new, I mean, that's where this is, that kind of type of programming problem. But once you get it, you will say, there's nothing. Okay. So I can, as I said, I can call the first one T0 or T1. I'm going to call it T0. So let me call it T0, T1, T2, T3, T4, T5. Okay, now let me go back and write the formula first. The formula is what? Vti plus 1 is Vti plus Ti minus, sorry, let me write the formula here. Vti plus 1 is Vti plus Ti plus 1 minus Ti times G minus C over N Vti. G minus C over M Vti. Let me substitute. So the first one, the first time I have is 5. So I will write V5 is V2 plus Ti plus 1 minus Ti is 5 minus 2, 3. G minus C over M V2. So you should know V2 is the initial velocity. Our assumption is that we know the initial velocity. So I will just say initial velocity is no, whatever that is. Usually we assume 0. Okay, the second equation V10 is V5 plus 10 minus 5 is 5. T minus C over M V5. V5, where V5, for us V5 will come, V5 will come from here. From the previous equation, we will get V5. And then V20 is V10 plus 10, 20 minus 10 is 10. G minus C over M V5. And then V35 is V20 plus 35 minus 20 is 15. G minus C over M V. Sorry, that's not V5. You're right. Probably that's what you said, but I'll check. V10. This will be V12. Okay, basically it is sequential, having to rely on previous values for the next values. Yeah, that is right. It is. Now, can you program this? I mean, that is what we are going to do. So we are going to program this. So you can just, we'll just convert this into program. First, there are 2 steps to program this. First, we will write an algorithm, which I will cover in the next class. And then we'll use that algorithm. You always, when you program, it is better to write an algorithm. So once you have an algorithm, it is very easy to program. So we will first convert this into an algorithm, which will be introduced in the next class. Then we nothing of a program, and that makes me what? Oh, you don't need to know anything. That's a good point. Here in this class, I'm assuming that you don't need to have any basic knowledge of programming. But you have to follow, especially this first lab is very important. You have to go through this Codecademy and you get as much comfortable as you can with this coding. But then, because unfortunately this course is not an introduction to programming. I mean that's something we are trying to fix. We will quickly go into advanced programming. So that's why I better. But I always I will take into consideration that some of you have zero knowledge in programming before. But all I ask you is, just follow me and then also work hard with that introduction C++ lab. If you have any question on the lab, let me know. That will just get you there. And once again, it is not a hard course. You'll be fine. I mean, if you had zero knowledge of programming, you'll be fine. Just I hope at the end of this class you have a good knowledge of programming. Okay. Any other questions? Yes, Abdullah.
Not a question per se, but an extension of what we've covered in the first part. For us winter starts, I've actually sent a schedule, like what our typical schedule looks like. So you can go through it for your reference when you meet with Dr. Azuz. So
Okay.
I've sent it on Outlook.
Yes, you can send that to me. I will
Yeah,
talk to you and find out what is this about overlap. I'll let you know. I'm not
understood.
sure how to handle this. But do you also have on Thursday as well? You have a lab on Thursday as well?
No,
Same time?
for Thursday, that spot is reserved. So when I registered for your course on UInsight,
Uh-huh.
it said lab will be on Thursday. Like there were no overlaps. So on Tuesday was reserved. It was reserved for physics, and on Thursday it was reserved for your class. But given your syllabus, there's an obvious overlap, and I've sent the schedule to you, so you can
Mhm.
use it for reference when you speak to Dr. Azuz.
Okay. Okay.
Yeah.
Yeah. I mean, yeah. I have both. In this class, we have both Tuesdays and Thursdays. So I don't know how they can overlap that, but I will find out. Is all our course material, including our labs for our entire semester, available right now? I'm not going to release right away because I always make changes progressively. I have last year's version, but I don't want to confuse you guys because I always make changes. So I will only release them progressively. All the material as we are there, I will release them, not right now. The reason is make small changes, and I don't want to confuse you guys. Okay, any other questions? Where do we find the record lectures? That's a good point. I'm just going to stop recording, and I honestly I never recorded lectures before, so this is something new for me. So it says recording in progress. Now let me stop the